We have Dr. Rima Habre, who I just met. It's wonderful, again, that you were able to come in person. Love it. Down from Southern California, USC. I see now that they have a Department of Environmental Health and Spatial Sciences. It's really kind of a cool way to think about it. And this is obviously going to fit in really nicely. Non-exhaust emissions and exposures and health risks, transportation. Thank you so much. Go ahead.
Good morning, everyone. It's so nice to be with you today. Thank you for the invitation. I will also say that Marianne and Mike are my personal heroes, so it's pretty daunting to follow them. But it's also very refreshing, coming from LA, going to LAX yesterday with Ubers and ride shares and, the mess that's LAX, coming to a setting where you guys think about really clean air and low levels of exposure. It's really refreshing and beautiful city. Anyway, so I'm going to talk to you today about non-exhaust emissions and how we think about assessing human exposures to them. Hopefully this is working well. And health risks. And I will say I tried to keep this somewhat high level, so it's not going to be a bunch of results, but maybe more of a conversation. Perfectly set up by Marianne's talk as well. So what are non-exhaust emissions? When we think of cars and transport and motor vehicles, we think a lot about what comes out of the combustion engine through the tailpipe, right? And there's been tons of work there. But what has been less sort of thought through or less attention paid to is these wear or degradation or abrasion particles that come out of brake pads hitting the brake discs when we brake, that come out of tires that kind of, abrade against the road surfaces themselves, right? Sometimes catalysts wear out of catalytic converters through the tailpipe. So this is a mix of a lot of different things. Most of these are very rich or heavy in metals, different kinds of metals. They're mainly coming out of these kind of mechanical erosion processes that usually will generate bigger particles, larger particles than we typically think of, PM 2.5. But because sometimes there's a lot of heat in braking, let's say, it tends to generate also very smaller particles that we don't think about as often. And so most of these are what we think of as primary emissions, directly emitted into air or into dust. But again, because we have these smaller particles and heat and all sorts of dynamics happening, we do get what we call secondary formation, or new particles, new pollutants forming from these really tiny ones. And so, they're heavily concentrated near roadways, like I'll show you, but also because they have this wide-ranging size distribution, they can travel other ways through air. They also can wash through rain or water and get into the ecosystem that way. So the other big difference is that non-exhaust emissions are generally not regulated the way tailpipe emissions are, at least, right? There aren't really emission standards on these things. You might hear them referred to in the literature as non-tailpipe emissions. Doesn't capture sort of the catalytic wear piece of it. They're also sometimes called abrasive vehicular emissions. And another key thing to note is that, I think in public health settings, when we talk about these things, it's all bad, right? But if you think about it, your tire is the only thing that's holding you to, that's the only contact point to the road, right? Brakes and tires are really essential safety features in cars, right? So we need them. They need to sustain a lot of very complex kind of functions, right? They need to operate in snow and heat and ice and LA and, Vancouver and all sorts of conditions. So there's been a lot of evolution and changes in the materials used to build these things over time. A lot of it is proprietary, so it makes our job a little bit harder to kind of figure out what's in them. But also it's not just sort of the chemicals in them, it's the different fillers and adhesives and, let's say, steel fibers and other sorts of things that are built into these materials to make them kind of meet the friction standards that they need, heat standards, all sorts of things, right? So that's important to keep in mind. And so let's say brake pads and discs started out with a lot of more metallic components, and over time they're changing. They used to contain asbestos, actually, and that went away over time. To more ceramics. Same with tires. The way we design them, what's in them is changing a lot. So this is a very nice figure that I literally borrowed from Dr. Hagino's talk, and that's a very nice talk if you're interested in this subject. But this shows you the regulatory evolution of what can be in these brake pads in Northern America over time. So again, we started with sort of asbestos in brake pads and quickly realized, thankfully, that that's a really bad idea. They used to have more steel and metal content, and over time that's fading away to what we call non-asbestos organic material, but that also kind of emits more things that could potentially undergo chemistry. And they have very notably high copper content, and there's been several regulations over time put in to remove that because we worry a lot about the copper toxicity. And so more recently we're moving towards sort of lower and lower copper content. The reason these kind of chemical profiles are important is because for us to do our job, to understand what people are really breathing and exposed to, we need something unique. Commonly what we call this is a tracer, right? To figure out how much is coming from these sources in our study. What can identify them or distinguish them from all the other things that we're getting from being near roadways or commuting? And so this is a table that just shows you some of the common or well-known markers of brake wear, and that's copper is a big one, barium, antimony, iron. Tire wear, we think of zinc as a really strong marker of tire wear. I believe we have talks on microplastics coming up and other organics and issues that are coming out there as well. Road wear tends to contain a lot of, let's say, silicon and calcium and crustal material that could also exist in kind of soil, but mixed in with asphalt and other types of, road surfacing materials. What we think of as a road dust suspension, so if you think of all these things being emitted along the roads and they settle on the road, and then as cars are moving and there's turbulence, everything gets resuspended again. So, in my mind, that's a mix of a lot of crustal, soil kinds of elements, plus a lot of the other stuff together. And, you're noticing mixtures are coming up as a theme today, right? That makes our job a lot harder to separate those things out and figure out what came from where and sort of what's the unique health effect of all these things together. And that's kind of the big point I'm hoping to drive through today. So again, a nice table just showing you some of the very common chemical markers that have been reported in the literature for these things. I will say I will focus mainly on brake wear today because I know others are talking about road dust and tires and other features of this. So as I mentioned earlier, so this very nice figure is from a famous paper that shows you what we call spatial gradients of pollutants emitted from traffic along roadways. So in that first plot, the first square on the left there, you see that for things like ultrafine particles and metals and carbon monoxide, they drop very quickly back to background within a couple of 100 meters, if I'm seeing that correctly. But then for larger particles and other kinds of pollutants coming out of the whole traffic kind of mixture, right, those are a bit slower to decay back to background. Why does this matter? Because as I was saying, all these non-exhaust kind of wear particles, they cover the range of size distribution. There's some that are very tiny, there's some that are very big, there's more that are very big probably, so it determines really how quickly they settle out of the air, where they're concentrated in space. And what's sort of another complication is they correlate or track very well with all these other pollutants coming from traffic, right? In different ways. And so that matters. We need to understand these things to figure out how to model how people are getting exposed to them when we're using these big models. It also matters from an inhalation exposure potential, right? And I'm sure this audience is very familiar with these kinds of plots that show, larger particles tend to settle in the upper airways, smaller ones, especially ultrafines, which we see ultrafine signals in these wear kinds of particles. They go very much deeper into the lungs, into the alveolar region. They can cross into blood circulation. They can, kind of make the rounds of your whole body very quickly. And another point I want to make is we sort of, let's say historically might have assumed that the larger particles, they settle in the upper airways, they get cleared quickly. You might swallow them and ingest them. Those are not too harmful. But it really depends on what's in them, and let's say features like water solubility of these metals and other things that could affect our health in different ways, right? So it's not just the tiniest particles that matter. And, it speaks to job security in a way, like Mike was saying. I'm not trying to be depressing, but the truth is, really the mixtures and components, like Marianne was saying before, drive these things in very different directions. The other point that Marianne also mentioned is that, we're seeing these great improvements in technologies, in regenerative braking, technology in hybrids, let's say in electric vehicles. They're leading to better fuel efficiency. They're actually reducing these wear emissions on a per car basis, if you compare an older car to a newer car. The problem, though, is that we have way more cars, right? And there's a lot of data now showing that these non-exhaust emissions are actually increasing altogether over time, probably as a result of VKTs increasing. That's the first time I've used VKT in my career. It's usually VMTs, and it's very refreshing. But anyway, so there's an overall increase, but the relative contribution of these non-tailpipe emissions as the tailpipe stuff is sort of getting cleaner, is also increasing a lot, right? So now when we think of the sort of traffic-related air pollution mixture, a huge kind of part of that is becoming these wear abrasion types of components. Another thing is that we haven't probably discussed much, and I'm not an expert in, but is also kind of a concern on top of the equity issues, right? Is that as these cars are getting cleaner, people want the bigger car, they want the SUV, right? The batteries are making them heavier, so braking-wise, that means more wear, and especially when you think about the trucks, right? And then there's the issue of lithium, and how are we getting all this lithium, and what's happening with mining around the world in different communities. I want to also point out Vahid's paper. Vahid just defended his thesis. He's done amazing work with Dr. Siuris at USC. He's also looked at longer-term data from LA and Southern California, and he's also saying, that we have seen reductions in combustion-related pollution from all these great regulatory sort of interventions, but road dust suspension, this part of the mix that's not coming from the tailpipe, is increasing in LA. And as I mentioned, zinc is a nice marker of tire wear, and the contribution of the tire wear source that he identified in the study. So we take a lot of measurements in Southern California. We speciate those, or we look at their chemical composition, and we can run some models that tease apart what were the major sources that contributed to that mixture. And so one of those sources you've seen is tire wear. And the contribution of this source to total zinc in the air, in I think this was PM 2.5, is also increasing over time, right? So it shows you that we have to really dig into the chemistry to figure out how these sources are behaving in general. Now, I want to step back a little bit and show you why it's, our jobs can be very difficult some days. How do we actually think about assessing human exposure, right? So, we can model pollution. We have amazing models these days of, let's say, concentrations right outside there. But when we are thinking about exposure, we're thinking, what are people getting in contact with, right? So there's that additional complexity of figuring out that contact point where people are actually breathing. So usually we'll start from thinking about a source. This is what we call the environmental health paradigm. And in this case, we're thinking a lot about traffic and, different kinds of vehicles, maybe the tailpipe, maybe the non-tailpipe or non-exhaust pieces of it as well. We measure concentrations in air. So as we've been saying, air is a mixture. Even PM 2.5 itself is a mixture. So we might collect these particles on filters. We might do some chemical speciation analysis to figure out how much barium and zinc and carbon and aluminum and calcium and all sorts of things are in that, right? And then there's some kind of an exposure assessment or assumption that we're making to link that pollution to where the people are. So that's the exposure. So if you see that kind of line, that's the body boundary. Generally the external exposure is happening right here where we're breathing, which becomes a dose, which potentially becomes a health effect. So what we do in this space, in the exposure assessment, and I'm overly generalizing, I have to say, right, is we use either measurements or models to kind of either get at that total mixture that people are breathing, let's say total PM 2.5, or how much PM 2.5 from traffic or from these non-tailpipe sources are they getting, right? Two very commonly used ways of modeling this are what we call source apportionment models. So these are saying we want to really figure out what's coming from the source, not just the whole mixture. Some of these are what we call source-oriented. So you start by the source itself, the cars. You might collect data on how many cars pass on a road, the weather that day, where is it blowing the wind, what are the emission factors for all these different things that we have information on, to some extent confidently, but to some extent not at all confidently, right? And you kind of follow the pollution. Where is it going? Where is it ending up? And then you figure out where the people are. The flip side of this is what we call receptor-oriented models, and that's starting with where the people are. We take measurements. So let's say here I might measure what I'm breathing. We run some analyses on those, and we run receptor-oriented models, like positive matrix factorization is a very well-known one, and we kind of backtrack or figure our way backwards to, okay, what are all the different things that contributed to what I'm breathing in the sample, at a general level, right? You can't get to exactly every little thing, but the biggest categories you generally can. So it really depends, where you measure those things, right? If I'm kind of what we think of as the gold standard in my field, at least for these external exposure assessments, is literally putting a sensor or a pump and a filter on someone and collecting what they're breathing right here, right? That's very difficult to do for everyone in the room at scale in these large studies, so we might approximate that by placing a sensor in the room that we're all sitting in, or right outside the building here, or on the rooftop of that building, right? That's all giving us information in general about population exposures or individual level exposures. Okay, I'm belaboring this, but I just want to sort of highlight how it gets very tricky. So there's a lot of these amazing models that are source-oriented. I'm going to walk you through some examples. For example, the R-line model or the Caline 4 model, it looks at roads as if they're lines, connected points, right? And it plugs in all these emission factors and weather and sort of spatial gradients and conditions about the road, etc., to predict where that pollution from cars is going. And I'm not sort of like, these are amazing models, they're helping us do wonderful things. I'm just highlighting where it gets tricky, right? These model the physical dispersion, not necessarily the chemistry, but that's also a huge plus. Where it's challenging, though, is, so this is a paper from colleagues of mine that shows you different maps of predictions of R-line PM 2.5, carbon monoxide, NOx, and different sort of ways to calibrate that to truth. Where it gets really difficult is if you think of an epidemiological model or a health analysis, we're usually plugging in an exposure to look at whether it varies with a health outcome, right? Adjusting for a lot of things. So if you were to plug in every single one of those exposures, generally the spatiotemporal patterns we're capturing with these models are very similar. I've actually looked at this with our own data. Like if I plug in Caline EC or Caline CO or Caline PM 2.5, they're 99% correlated. So really, I could see an effect with any one of those with my health outcome. I don't really know if it's the EC or it's the NO2 or it's this or that, right? Because the inputs are all very similar, and if they're different, it's sort of a scaling difference. It's not really in the correlation, it's not translating with these patterns that we're seeing. The other approach to doing these that is also super useful is receptor-oriented models. So we've done some work in Southern California, in LA, and these measurements were collected back in 2008 and 2009. So things are very different now, but they were very useful to let us sort of see what's in these mixes. So, my colleagues, even before I joined USC, collected speciated PM.2, what we call quasi-ultrafine particulate matter samples, PM2.5, PM10. So small to kind of mid-sized to very big particles in 8 different communities in our children's health study in Southern California. And we speciated those for chemistry, and I ran these source apportionment models, and we were able to actually detect different signals in those samples for tailpipe and non-tailpipe or non-exhaust emissions. Generally, we saw the common sort of elemental carbon, organic carbon, boron, which is a lubricant that's added to gasoline, come out into these tailpipe signatures. And we also saw the non-exhaust or the non-tailpipe brake wear, tire, and catalyst wear signals coming out, and those markers were the same ones that I showed you earlier. So barium, copper, molybdenum, antimony, etc., and some of the catalysts. And so just to show you, the reason this is not a big deal, but like a very interesting study, is that it's been really hard to show how these abrasive emissions or these wear emissions kind of come out separately from the whole tailpipe mix so far. And because we've had really expensive, honestly, analyses on these filters that are more sensitive with detection limits, we were able to see this. So overall, the reds kind of shades of red are either traffic altogether or when it separates into diesel or gasoline. So if you look at let's say, that middle plot, that's PM2.5, and we see that gasoline traffic, tailpipe traffic, was contributing 15% to total PM2.5 mass in the study. Gasoline traffic was a little bit less than that. Again, this was older in LA, so Long Beach was a very huge driver. If you know Long Beach, it has massive ports and truck activity and diesel trucks, etc. But the really interesting thing is that first top sort of blue box, the abrasive vehicular emissions, or these wear particles. We saw them come up in the quasi-ultrafine, the smallest, in the fine, and in the coarse PM size fraction. And so yes, they're a big chunk of the PM course. I can't see correctly from here. I think that's an 18%. But 11.4% of the mass in the PM2.5 size fraction was these wear particles, and in the ultrafine size fraction, right? The fraction that gets very deep into the lungs. This was very different across communities, so it kind of tracked well with where we know the heavier, let's say, warehousing, freight, truck activities were happening. So let's say in Long Beach, you see that abrasive vehicular emissions were probably 60% of the coarse PM mass in that community. And, we've known a lot about sort of traffic impacts on respiratory health, on cardiovascular health, on all sorts of outcomes in these communities. But where we have a hard time figuring it out is how much of that is sort of the tailpipe versus the non-tailpipe or non-exhaust chunk. The other part that adds complexity to this is we ran sort of these very flexible models to try to figure out, okay, if we wanted to even try to model these wear emissions or wear contributions, what are some commonly used geospatial metrics that we might have available to us that can predict the variation in these things? Now, the interesting thing is if you look at the quasi-ultrafine wear source, that correlated very highly with higher number of intersections within 500 meters and higher what we call non-freeway highway, or let's say, the smaller roads, not necessarily the freeways and highways in LA, NOx pollution coming out of the tailpipe from those roads, right? So we use the Caline model, which is the dispersion model up on top, and intersections, and you see this very clear, strong signal that's having removed Long Beach because it overwhelms everything with all those trucks in Long Beach, so in all the communities. So it's very nice because we can see these trends, and we hypothesize, let's say, that more stop and go and more kind of cars and emissions on the roads in general should lead to higher abrasive vehicle emissions. The only thing that you're not seeing here is that most of these tailpipe and non-tailpipe sources correlated in one way or the other with one of these geospatial metrics, right? So even if, it still means we don't have anything too unique to pick up on these if we want to model them or predict their concentrations kind of at a larger scale. Okay, oops, I'm going the other way, sorry. So I want to move us a little bit more to kind of thinking about the person and what we could do at an individual level, knowing that we're a long way from being able to do that at scale, but we're developing a lot of these cool approaches now. So this is work from our Madre's pregnancy cohort in Los Angeles. We have an Environmental Health Disparities Center that's led by Carrie Breton and Tracy Bastain, and I lead what we call the exposure arm of that work and several different projects. And so this is a cohort study that we're recruiting through hospitals in the heart of LA, so it's a very urban environment from these hospitals, and you can see sort of the neighborhoods where we have the most women recruited from. In some of my studies, I do what we call personal exposure monitoring. We have this purse that you see all the way on the right that has a pump in it, that has filters attached to it. The sampling inlet is right here in the shoulder, and we give these purses and sampling devices to pregnant women in their third trimester. We do this sometimes in earlier and later time points, but we collect very personal exposure data. And so in some cases, like you see on the left, we collect very time-resolved sort of minute-level exposure information. We tie that with 10-second GPS, so we can really track sort of the exposures with where and, when these things are happening. And we also collect filter samples that help us do some chemistry. So this is the work from my postdoc's, now postdoc, formerly student Yan Xu. She did a very nice thesis kind of analyzing these personal PM 2.5 exposures that these pregnant women were exposed to. And so what we did is we take their GPS tracks, that's all the way on the left there. We draw what we call activity spaces around them. So there's different ways to do this. Some that are more resolved, some that are coarser. And so, for example, if you look at the nice color gradation, or actually the plot on the bottom that's reflecting that nice color gradation, we use kernel density activity space methods to basically follow the GPS track in space and draw where they've been. But we give much higher weight to places where they spent a lot more time in, right? Versus assuming that they're equally exposed to everything they see, in places that they've quickly passed through, let's say. And so she collected a lot of other information as well and threw that all into a model to predict personal PM 2.5 exposure as a whole in the breathing zone. And I'm not going to show you all the other results, just to focus in on today's topic. But basically, she saw that having more primary roads within this KDE area that we drew and more secondary roads was associated with significantly higher personal PM 2.5 exposure. Do we know if that's from wear or from tailpipe? No, we don't, but it's a very kind of important way to link to what people are actually breathing. The flip of that was also true. Seeing more greenness and more park area within these activity spaces was significantly associated with lower personal PM 2.5 exposure, and that to me is also a very nice confirmation, to policymakers, let's say, like, see, if people actually spend time in these things, what they're breathing goes way down at the end of the day, after taking everything else into account. To get a little bit more at the chemistry, so she also took the chemical composition data that we analyzed on these filters, and I'll say we didn't have as much money for this one, so we only used XRF, X-ray fluorescence, not as sensitive as the earlier methods, but still very powerful. And she detected these six sources of personal PM 2.5 exposure. And if you think about it, we're all exposed to a lot of different things. It's not just traffic, it's not just wildfires, the carpets here are emitting VOCs, the paint, etc. So a lot of things about what you do day to day really affect what you're exposed to. And she saw that as well. So there were secondhand smoking variables that had these characteristic brown carbon and other markers in them. There was a crustal source, aluminum, calcium, titanium, things that are kind of suspended by dust as you walk, fuel oil, sea salt, etc. But traffic came up as a source in these personal samples. It did not contribute the majority to the final mass that these women are breathing. And that's a nuance also. We kind of tend to think of these things as like it's going to overwhelm everything. No, there's a lot going on in daily life, right? But we still detected that, even if it's a low contribution. Sorry, just to go back and highlight. So black carbon, which is a marker of these kind of tailpipe emissions typically, right? And barium and zinc, which are markers of some of the wear particles, were the characteristic features of this source. What we did next was to try to understand, is this really traffic? What's correlating with this? It's a little bit, with these things, it's like you're putting together a puzzle. You're working your way backwards. And so actually the very interesting thing first was, are these sources even correlated with each other? When you're exposed to traffic, does that correlate with exposures to other things? And the traffic source itself was moderately correlated with this crustal source. So crustal is again sort of like soil or resuspended dust that you might be exposed to. So if you think in LA it's very dry, it doesn't rain as much, you could be walking on the street suspending dust and also getting traffic. That happens. It's not sort of out of the imagination, right? It could also be that maybe it's some road dust signals getting mixed into this. Who knows? But that in and of itself is interesting, that sometimes different things correlate with each other. But she also looked at, do other factors sort of predict or correlate with this personal traffic source? And we looked at the data we have, so we know where every woman lives, and we can assign a lot of different sort of exposure metrics at the residential level. And we looked at the ozone data, the NO2 data, the PM2.5 data that we have assigned outdoors at the residence. And sure enough, we see a negative significant association with ozone. So we know that fresh traffic emissions kind of react or quench ozone, right? They make ozone go down, so that makes sense. They were also very highly correlated with outdoor NO2 levels. We think of NO2 as a marker of tailpipe traffic outside in ambient air, right? So that makes a lot of sense. And also, interestingly, this Caline 4 line source dispersion model that's just giving us, how much NOx is coming from nearby roads outside that house, theoretically modeling tailpipe emissions, right, is also significantly associated with all these other road measures within the activity space. So the big picture is, it's very impressive that we can even see this, and we're starting to have methods to kind of pull apart these signals. It's still very hard to figure out what's the unique thing that predicts them, predicts your exposure to them when you're in a near roadway environment, right, or in general life. I think I'm close to wrapping up, but I just want to talk a little bit about, health risks and kind of broader considerations at a very high level. And so, as I was putting together this talk, I was really trying to think, so what do we know now? We know these things are going up a lot. We have a very well-established epidemiological literature on the adverse effects of traffic-related air pollution, using different sort of measures like NO2, like some of these line source dispersion models. We don't have as much on these non-exhaust exposures. In fact, I'm not even sure, I don't remember seeing a direct epidemiological study, maybe they're out there, but relative to what we know about these tailpipe emissions, very little, if anything at all. This very high source collinearity or correlation between all the different sources that are affecting your exposure when you're in these traffic situations, right, makes it very hard to separate out these signals in terms of, what are these wear emissions actually doing for our health that is not what the tailpipe emissions are doing, right? And so I think we're getting there. I think the methods are improving, and, potentially, like Marianne showed, with a lot of the sort of GPS activity modeling and trajectories paired with some of this chemistry, we're getting there with very sophisticated methods, but we haven't yet been able to do this sort of at large scale. There's a lot of very interesting toxicological studies, in vitro, in vivo analyses, or experiments, all pointing to negative effects of these wear emissions. So they might isolate, let's say, certain samples from dynamometer studies or other kinds of studies, really taking those exposures, doing something to them, exposing mice or cells, etc., they're all showing very adverse effects that we know are associated with air pollution exposures in general, right? It's hard a little bit to translate that to what you might experience in the real world, but the toxicological evidence is there that these things are harmful. And again, we don't need to reinvent the wheel in a way, because what we know about how PM is bad for you also applies in this case, right? These are particles that span the whole size distribution. They're very heavy in metals and other kind of proprietary chemicals that we're not even sure what they are yet. We do need to think about high-risk subpopulations, and so that means there are groups and communities and individuals that get way more disproportionately higher exposure to these things that we don't yet know what is that doing to their health. So if you think of, rideshare drivers and Uber drivers, they're on the road every day, right? If you live or work near major roads, and this is very common in LA, you see, for example, a lot of the low-income housing or schools sited very close to major roads, and it's a big issue. If you have existing health concerns, and of course, EJ communities. So again, Marianne pointed to this, but in LA, what happened in the pandemic is, shipping and e-commerce went off the rails, and the ports of Long Beach and LA were not keeping up anymore. You had truck activity, morning, night, every hour of the day, really pushing the residents' kind of cars out of the way. I mean, there was real friction there with the community, but the entire freight goods movement corridor upped its activity. I don't know exactly by how much, but by ridiculous amounts, right? So there are always communities that are getting the bigger brunt of these exposures that, again, Marianne very nicely showed. And so I just, to kind of sum it up, and a lot of very nice reviews papers, talk about this. We know a lot, but we still don't know a lot, if that makes any sense. And it's still very hard for us when we're doing epidemiological studies to be able to isolate the effects of these these wear emissions from the tailpipe emissions in health contexts at least. So more work to be done. I think I've said this enough already, and I do want to emphasize that we have amazing improvements in sort of modeling chemical transport models, fusing those with dispersion models, with machine learning. We're getting there, but we're still struggling with this source code linearity issue. Given that we're also seeing these things are going up over time, and seeing people jumping to electrification is everything, at least in LA, and that worries me. We really need to be thinking about what's happening here, and hopefully we can slow down and think a little bit. Anyway, I think that's it for me. Thank you so much. I hope that was interesting.
Okay, we're just kind of entering into the break time, so we might have to keep it a little bit short, but I would definitely entertain the so-called burning question. I didn't see. Go ahead, Marianne.
First, thank you very much for just highlighting the complexity of studying non-exhaustive. I think right now a lot of complexity and a lot of things we don't know. It was interesting what you said at the end about I do a lot of air quality modeling, and I think we have systematic emission profiles for non-exhaustive emissions so that we can generate exposures to the load. But a lot of the literature we've done points to the fact that we don't have that, right? We don't are not at a stage where we have systematic information to input into air quality modeling. So my question is, it looks like we're now starting from scratch, like we were studying the impact of air quality on how we're now doing air quality modeling. We see ATI funding a lot of a lot of proposals of doing studies. Maybe they could just do like a high level 2-minute pitch. Is there can we do it better than the way we've done with just discovering air quality? Is there a more systematic, more collaborative way in which we can just run all these studies? Because right now, different studies just
Thank you, Marianne, and that's exactly the heart of it, I think. You're right, emission factors are very noisy and very difficult to pinpoint. I think there's a little bit more work these days. Vahid, who is actually a wonderful student, has done some of it, but people are starting to do more kind of accurate emission inventory, emission factors work. It still worries me when we plug those into our models with other things. You know, the output will correlate with what you put in, right? And most of these traffic signals, you know, are kind of coming from the same origin in space and over time, etc. Can we do it better? I think it's kind of like your last slide, right? The book that you showed, which is so awesome. You know, sometimes I puzzle, honestly, in this world, like, we always seem to want to reinvent the wheel. You know, do we need to know, like, do we need so much global burden of disease work to know that these things are going to be harmful? I don't think so. You know, like, it's pretty obvious. I also don't know that I have a great answer, to be honest, but I think something that the EU does better is think about chemicals and chemical structures and how we let chemicals on the market. They kind of pre-think, like, if it looks like it's going to be bad and it acts like it's going to be bad and it has the structure of something really bad, it's probably going to be bad, you know? So can we pre-mitigate some of that? So I think it's also very difficult with, as you know, right, the need for production and commerce and the sort of manufacturing side of things. So I honestly don't have a satisfying answer to that, but I agree with your frustrations.
Please take this gift.